Good morning. I'm Liz Goldsmith from the TIA's Fiber Optics Technology Consortium, and I'd like to welcome you to this morning's webinar, Optical Trends in the Data Center. Presenting today will be Doug Coleman from Corning Optical Communications. Before we start, I'd like to cover a few housekeeping items. Our web conference is scheduled to run for an hour and 15 minutes. Our presenter plans to answer questions at the end of the conference, but please feel free to submit questions at any time by using the Questions tab on the top of your screen. Audio is available only through your computer. Occasionally, people have trouble with the audio coming through clearly, but it's always been just fine on the recorded version. So if you have any problems, please listen to the program on demand. It will be available later today. Attendees of both the live conference and the on-demand version will receive one VCSEL continuing education credit for participating. Please email me, Liz Goldsmith, at liz@goldsmithpr.com to facilitate the issuing of the CECs. And don't worry, my email will come up at the end, so you won't have to write it down now. Please be patient. It takes us several days to process the CECs. Now, let me tell you briefly about the TIA's Fiber Optics Technology Consortium. The TIA FOTC focuses specifically on structured cabling. The section was formed a little more than 20 years ago as part of the Fiber Optics division and was originally called the Fiber Optics LAN section. Our mission is to provide vendor-neutral information about communication solutions using fiber optic technology. Our members have traditionally been a mix of fiber manufacturers, cablers, and manufacturers of test equipment and electronics. On our website, www.tiafotc.org, you will find fiber FAQs, standards information, articles, past webinars, presentations, white papers, and industry research that we've conducted. We also have a free network architecture model that you can download to compare the suitability of different standards-approved architectures for your installation. For those of you interested in listening to past webinars, a full list is available on our website and on our Bright Talk channel. Please make sure that if you want to earn CECs, that you are on the TIA channel, as other companies may not offer continuing education credits. Our most recent webinars include design and deployment best practices for reliable industrial fiber networks, beyond bandwidth, managing assets in today's fiber network, understanding the healthcare facility standard, NCTIA 1179, and getting it right the first time, reducing the time and cost of retesting. You can watch these web conferences on demand at this Bright Talk channel and find direct links to each webinar on our website. Now let me introduce Doug. Doug Coleman is Manager, Technology and Standards, and Distinguished Associate for Corning Optical Communications. Doug has 35 years of experience in the optical communications industry and speaks frequently at industry conferences. Doug?
Well, good morning. Many thanks to everybody for participating in today's webinar. These are exciting times for optical connectivity. And my objective today is to share with you technology and standards activities that have or will enable fiber to be the primary connectivity media that will be used in data centers configured for operation at 10 gigabit and higher speeds. The first slide we have here is sort of my bread and butter slide that I've been using through the years because it really sets up exactly what our end users are looking for in the physical layer solutions that they want to deploy in their data centers today. Looking at the bits there, the bullets on the left, you see that they're looking for a media type that enable them to support not only legacy speeds and current speeds, but they also want to be able to take that existing physical layer and be able to migrate it to the emerging data rates that we see coming out there on the Ethernet Alliance roadmap, speed roadmap. And with what we know today about the distance considerations, we can effectively design physical layer solutions today that can adequately support lifetime cycles of 15 to 20 years without having to significantly reconfigure that physical layer solution. On the next bullet, our customers are looking for very high density solutions, not only in pathway spaces, but also in the vertical and horizontal management within the racks, but also are looking for very high density solution in the electronics. This is really helping to enable the use of optical connectivity even greater, as it's been able to support a higher port density on the line cards that helps drive down the overall cost per circuit. So density is important from pathway and space, and it's also important from electronic density capabilities. And also we get into reliability. We all clearly understand that our data center has to stay up and running, and optical connectivity with the bend-sensitive performance features that it has is a very robust medium. A lot of people still consider fiber not necessarily as a robust media, but when you look at apples to apples, it is probably the most robust media out there mechanically as well as environmentally to ensure long-term reliability and performance. And then end users want to maximize their capital and operation expenditures. And then finally, from a green perspective, everybody wants to minimize their overall environmental footprint. And with the optical connectivity out there, it uses significantly less raw materials in the fabrication of the connectivity solutions, and also uses less power, and also provides optimized cooling within the data center, as it has much higher density within the pathway spaces. So moving on, when we look at the data center today, there are obviously two options as to what type of transmissions you're going to do, either on single mode or multi-mode fiber. And what we traditionally see is in the enterprise space, multi-mode fiber continues to be the predominant connectivity solution being used, where hyperscales are now migrating to single mode fiber to address longer distance needs. So on this slide here, I want people to clearly understand why people continue to use the multi-mode fiber, and it's all driven by the value prop associated with the multi-mode fiber transceivers. The light source that is used is a VCSEL, as I'm certain you're quite familiar with, and these VCSELs are very easy to fabricate, test, and they're very easy to package into the transmitting optical subassembly of the transceiver form factor. And what this results in is the relative pricing that you see on the left side. So I have provided, and these are current as of today, based on the relationships that I have with industry manufacturers. These give you a perspective on what the relative price differences are for 10 gig, 40 gig, 100 gig, and the new 100 gigabit using the 25 gigabit lanes. So you can see it's the actual price of the transceiver that enables multi-mode fiber to offer significant value prop in addressing distances of 100 meters or less, while we see single mode migrating for use in distances beyond 100 meters when addressing data rates of 100 gigabit and higher. So this is a slide that I update annually that gives you a perspective on the fiber types that Corning is shipping into the data center. So this data here is inclusive not only to the enterprise space, but also the hyperscale space. And you can see that the purple and the light blue represent OM3 and OM4 fiber. And you can see that over time, OM3 and OM4 have gradually increased, and we're seeing more increase of OM4 over the last couple of years. That is a result of OM4 being standardized in TIA and the international standards with the detailed fiber specification standard. And also with the fact that the transmission standards just recently are now using OM4 for setting their distance objectives for data rates such as 32 gigabit fiber channel, 128 gigabit fiber channel, as well as the recent 100 gigabit 100 meter distance as well for 802.3 BM. An interesting aspect here is that single mode up to about 2013 has remained pretty flat, where in typical enterprise spaces, single mode was only being used for carrier interfaces as well as uplinks within colo data centers, and some colo data centers as well as some applications where FICON is being used. But with the emergence of hyperscale, you can see how the overall growth of single mode has grown in 2013, with more and more single mode being used in these hyperscale type data center locations. So these are the respective distances that are specified within the standards for the OM3 and the OM4. So I have fiber channel up here, and I have the Ethernet. So OM3 first emerged with the development of the 10 gigabit standard. You see there it goes 300 meters. So in the first release of the 10 gigabit standard, there was only guidance for the OM3 fiber. But later on, there was an addendum to the standard to include OM4 fiber, and you can see I have two distances there. The standard specifies 400 meters, but we're all quite aware that many companies out there are specifying 550, and that 550 would be defined as an engineered length that defines what is specified with the actual 10 gigabit standard. So we move on to 40 gigabit and 100 gigabit, and you see the respective distances of 100 meters for OM3, and the OM4 is 150 meters. And then we have the new recently completed 100 gigabit standard using 25 gigabit lanes showing 70 meters and 100 meters. Something interesting associated with these distances is that both Ethernet and fiber channel in these distances assume a 1.5 dB total connector loss. With the exception of the OM4 distance of 150 meters, that assumes a connector loss budget of 1 dB. Now, periodically I get questions as to understand why the first generation of 40 and 100 gigabit only go 100 meters when the native 10 gigabit standard went 300 meters. The reason for that is the 10 gigabit optics that are used for the parallel optics of 40 gig and 100 gigabit use less constraint, reduced performing 10 gigabit optics, and that was done as the standards community felt that the 10 gig guidance at 300 meters was way over engineered. And after the 10 gigabit standard was done, a multitude of companies went out and investigated actually what the length requirements were in a data center for multimode, and it became pretty conclusive that 100 meters met around 88 to 90% of those lengths. So once that data was presented both at Ethernet and fiber channels, these transmission standards groups started using 100 meters for setting their distance objectives for multimode fiber. So as I alluded to earlier, once the OM4 fiber was standardized into a detailed fiber standards, we started seeing the transmissions groups using OM4 fiber for setting the distance objective of OM4 fiber and using that for 100 meters. So this is just an example of a transceiver manufacturer, Finisar, who made a proposal during the emergence or the development of the 32 gigabit fiber channel to use OM4 fiber performance attributes for defining a distance objective. And it was not only used for fiber channel, it was also, as I said, used earlier for the Ethernet guidance for 100 gigabit using the 25 gig lanes. So people are now asking, or we're getting on the copper treadmill. Everybody's quite familiar with the copper treadmill where you had category 3, category 4, 5, 6, 7, and so forth. They're wanting to know, well, if I put in OM4 fiber, does that mean eventually you're going to come out with a higher bandwidth fiber for OM5? And the impression is that, no, this is not necessarily going to happen, because as we get to the higher data rates, we're not really becoming limited by the modal bandwidth of the fiber. We're becoming more limited by the chromatic dispersion performance of the fiber in the 850 nanometer range. What you see on this slide here is a typical chromatic dispersion curve, and what it shows is that at 850 you're seeing a typical dispersion of around 84 picoseconds per nanometer dot kilometer. And this becomes quite excessive when you start looking at data rates that are using 25 gig and higher speeds, because in transmission systems they're normally limited to a rule of thumb of 30% of the bit period. So with 10 gigabit, the bit period for 10 gigabits is 100 picoseconds. So if I take 30% of 100 picoseconds, that tells me I can tolerate up to 30 picoseconds of chromatic dispersion, which is effectively done at 10 gigabit with no issue. But once you get to 25 gigabit lanes, you'll see that 25 gigabits translates into 40 picoseconds of a bit period. And at that bit period at 30%, that only allows you 12 picoseconds of chromatic dispersion. So this drives the need potentially for pursuing an optical fiber that be able to support multiple wavelengths across a higher wavelength region to be able to support higher bandwidth or system needs. So this is an example of what chromatic dispersion is. When you have an output of a pulse into an optical fiber, it's not necessarily monochromatic. It doesn't necessarily just have one spectrum of light. It can contain different spectrums of light, and due to the difference in the refractive index, as that light propagates down through the optical fiber, the pulse will spread due to the different transient times of the different colors of light. So this is just an illustration of what that chromatic dispersion term means. So just to elaborate a little bit more on why it really doesn't bring much value to continue to increase the modal bandwidth at 850 nanometers, this is a chart that gives you an understanding of what the additional distance gains are for when modeling 28 gigabits, which is representative of 32 gigabit fiber channel. When you look at the transceivers that are used out there for multimode fiber, the typical spectral widths that are used now fall between 0.45 nanometers and 0.65 nanometers. And when I model that spectral width with the use of an OM4 fiber using 4700 megahertz fiber, you can see that I have a distance capability of 100 meters at 0.65 and 130 meters at 0.45. So people would sometimes assume, well, if I throw more bandwidth at it, it will obviously give me greater distance capability. But what it shows is if I put a 10 gigahertz multimode fiber on there, I only really gain 5 meters, and at 0.45 I could only gain 40 meters. So it really doesn't bring much value to continue to increase the bandwidth at 850 nanometers due to the excessive chromatic dispersion penalty that is occurring. It really only brings value with higher bandwidth at 850 if the VCSEL manufacturers are able to implement tighter spectral widths on their VCSELs. And it's my understanding, due to the aperture size of these VCSELs that are used at these higher data rates, it would compromise the overall reliability of these sources to operate them at spectral widths much lower than 0.45. So, in summary, going to a higher bandwidth at 850 really is not going to add much value into the system. It leads to the fact that we need to start looking at WDM systems to support higher bandwidth capability. So this gets into a slide that was presented at ECOC back in 2013, where Avago made a proposal in response to the topic that I just talked about, that the increase in the modal bandwidth really brings no value, and you need to start looking at doing WDM or CWDM performance on the multimode fiber. So these are some of the bullets that they presented. What's important here is that looking at target wavelength range in their proposal ranged between 920 nanometers out to 1,000 nanometers. And that's important is because the VCSEL technology that is used today, the material science associated with those VCSELs can, I'll use the term easily, and it might not necessarily be construed as really easily, but it's a lot simpler to tune a VCSEL in that range with the existing material science versus going to much higher data, higher ranges, which require some extensive material science for able to accommodate that. So just this past October, an initiative was made at TIA to pursue the development of a wideband multimode fiber. These are some of the objectives and considerations that are being evaluated. They're looking to develop guidance on a multimode range that's 100 nanometers in length that would fall between the 850 nanometer to 1100 nanometer range. The objective is to be able to support 2 to 4 wavelengths, as well as operations of VCSEL transceivers. You can see the data rate that they're looking to be able to support is being equal to or greater 28 gig to be able to provide 4 wavelengths that would be able to support up to 100 gig. And also you can see a distance objective that they set out there for 100 meters. What's very good about this group is that it's not necessarily made up of fiber manufacturers and cable manufacturers. We've also have gotten the VCSEL transceiver manufacturers engaged, such as Avago, Finisar, and JDSU, who are providing very valuable insight into the transceiver performance attributes that help drive the wavelength range and other performance attributes. I just got an update. I just saw an update today on when they expect the first draft ballot to be coming out, providing guidance, and that will be January 2016. My own personal opinion is that I don't think this activity will be completed until about January 2017 at the earliest. Some examples of long wavelength sources out there with VCSELs. So you can see that 1060 nanometer VCSELs are commercially available today. Actually, VCSELs are really optimized for operating at the higher wavelengths. They consume lower power, and again, you see lower power dissipation, which translates into higher reliability. And then on the bottom, you can see some activity that's taken place in the industry where they're looking at silicon photonics operating in the 1310 region and launching into multimode fiber as well. So moving on to the trends in the data center, the focus relative to the electronics as well as the connectivity solutions are all focused on enabling low-cost solutions, very low power considerations for the electronics, as well as providing for connectivity and high-density solutions on the electronics. So this is a roadmap for VCSELs, and what it shows is that today, when you buy a chassis switch or a top-of-rack switch, you can see on the very top there, the red box represents the interface for a pluggable transceiver module. So you would take something like an SFP plus or a QSFP, depending upon what data rate you're running, and the optical signal would come into an electrical connector. First of all, it would come into the ROSA that would convert it over to an electrical signal that would then hit an electrical connector that would then run the signal across an electrical trace out to the board host chip. And that slide at the top is there to show that when you're running fairly low data rates of 10 gigabits, you can have a nice long electrical trace that runs from the host chip out to the optics without having to really be concerned about any type of electrical discontinuity or aberrations or penalties that have to be corrected for. But as we move on to these higher data rate speeds, such as 25 gig, where we have 25 gig electrical signals running from the host chip out to the pluggable module, there are aggregated penalties or errors that can accumulate across that electrical trace out to the very front of the bulkhead of the switch. And you can either plug in a transceiver module, but you might have to accommodate certain integrated components in there to correct for distortions on the electrical signal coming off the host card. But some people now are also considering using embedded optics, where in the second image down, you can see where the optics is actually embedded onto the host card of the electrical switch. And by doing that close to the host chip, you minimize the length of the electrical trace, which minimizes the electrical penalty or distortions across that trace that have to be addressed. And then you have an optical pigtail that comes off the embedded optics that runs out to the front plane of the switch, where you would plug in with typically a MPO connector. Then going down further onto the roadmap of this chart, you can see that the optics then are removed from the host card itself and are actually embedded onto the substrate of the host chip. So once again, it just gets it closer and closer to the chip to mitigate any penalties from the electrical to the optical domain. And then forward on, you can see that we have chip-to-chip optical pigtails where the optics are actually integrated into the top of the chip. And then finally on the bottom, you can see where the optics are actually integrated into the chip itself, and we're using optical waveguides that then focus out to the front plane for the interface to the MPO type connector. So this is a nice roadmap to get a perspective on where the switch manufacturers are going. I firmly believe that the traditional design will be the dominant solution used for at least another 5 to 10 years, but we could start seeing some embedded optics on some host chips and traditionally high-density router systems for short-length interconnects. On the bottom two down there, we'll probably start seeing some of that when we start getting to 56 gig type electrical lanes, because we're really going to be limited on the electrical trace when we start doing non-return to zero electrical traces from the host chip out to the front of the card. And in a router environment, that would be very conducive to use NRZ for short-length interconnects with that pigtail out to the front, because NRZ versus something like multi-level encoding uses less power. So this is an example of a commercial available product out there using embedded optics. You can see in the image on the right where you have these transmission and receiving embedded optics attached to the host card. So in this image you have one embedded optics where you have 12 lanes of 10 gig or 25 gig channels coming out of a transmitter, and then on the other side of it you have the receiver that would receive 12 lanes. With 25 gig lanes, 12 times 25 would give you 300 gig. We had a capability that could go out to the faceplate that then could be broken out to 3 100 gigabit circuits. So it provides for a lot higher channel density and circuit density as well by using embedded optics. So inconsistent with the roadmap that we saw here, here's an example again from another company that we have the optics actually mounted onto the substrate of the switch chip. So the roadmap, I just want you to show this is actually real, and people are actually developing products in conjunction with that roadmap option that we saw a couple slides earlier. So this is just a global statement that sort of what I talked about earlier, is that pluggable transceivers will continue to be the dominant method being used out there in the data center, because it does offer you a pay as you go type solution for typical type uplinks from the edge out to the core. But embedded optics probably mostly you'll see some traction being used in high performance computer type applications, as well as doing short-length interconnects between routers within the data centers. So the discussions that we had just then were relative to multi-mode and single mode in the traditional type switch world, but now we have the emergence of silicon photonics. So this is a typical type silicon photonics chip that has all the components of a transceiver integrated onto a wafer and or a chip, and all the components that are fabricated onto this chip during the manufacturing process, and essentially the only component that is missing from the wafer to enable its functionality is a light source. So you can see there on the bottom left that with this chip here you have to integrate a DFB light source that then launches the light into the chip, and then it's modulated and then transmitted out of the transceiver into the optical fiber. But similar to the multi-mode and legacy single-mode solutions, they're on a similar roadmap. So in the top left there, you see that they'll use the silicon photonics for pluggable modules in the top left that could plug into a top-of-rack switch or a chassis switch, either into a row or in a core switch back in the main distribution area. Or it can be placed in the middle image you see there with embedded optics around the switch chip. And then on the bottom right there, you can see where they can also take their technology and integrate it into a switch chip as well. So people are looking at different means to be able to support this roadmap out there with switches of the futures with the different transmission or transceiver types out there that can be used to accommodate their needs. So this is a well-known slide that I'm certain many people on the call today have seen, and whether or not it's all that accurate, it's probably reasonable. But the reason I use this slide is that I think it's important for people to understand where the high data rates are coming from in the data center. The blue line there represents the I/O link down into the servers. And with server virtualization that's taking place right now, we're seeing multi-core CPUs being developed or being deployed on servers requiring significant 10 gig, 25 gig, 40 gig drops down into the server. And when I'm running at that type I/O speed into the server, it drives the need for higher uplink speeds from the core out to the edge. So that drives the need for 40 gigabit and 100 gigabit uplinks to be able to support those 10 gig, 40 gigabit drop links down into the server. Not only does the core have to be able to support the uplinks out to the edge, it also has to be able to support the higher data rate speeds that are coming into the data center from the outside carrier world. So simplistic discussions about server virtualization. In the past, you would have a rack mount server in your data center, and each one of those servers would be supporting a single application. And when you have that type of a deployment, the overall utilizations of servers under those conditions were very, very low. They would have utilizations of less than 10%, 5%. So to maximize use, sometimes they would try to increase the CPU operating frequency to higher ranges, but that resulted in higher heat and reliability concerns. So to increase the overall utilization of servers, they went to multi-core processors. And with the multi-core processors, it enables, and you can see in the slide right here, you're able to have CPUs that can support the range that you see up there today available are 4 and 18, 16 cores. And each one of those cores has a processing capability of around 2 gigahertz, which translates for 16 cores into about 32 gig of processing capability. So at 32 gigabit processing capability on my server, that means my drop from my edge down into my server would need to be based on my oversubscription. It could be multiples of 10 gigs, or it can be a 40 gigabit, or in the future could be multiples of 25 gig. Other things that enable the server virtualization is the use of PCI Express. They're going to higher lane speeds from the NIC out to the CPU, and they've also increased the overall memory capability of the servers also to address the multiple VMs that are operating on the servers. So by integrating all this together, where servers of the past were operating at rates of less than 10%, we're now seeing people designing these servers to be able to have utilization rates as high as 90%. So this is a nice roadmap of the lane speeds that are being used in the Ethernet community, and that also feed into the servers as well. So when you look at the green on the left there, you can see that with 10 gigabit with one lane, I can do duplex fiber transmission with 10 gigabits in both directions. I can take 4 10 gigabit lanes coming off my electrical card to get 40 gigabit one direction, and take 4 lanes to do the receive in the opposite direction, thus requiring 8 fibers. And then for the first generation 100 gigabit, they were using 10 gig lanes with 10 lanes of 10 gig in both directions to get 100 gigabit. So with multi-mode fiber, that was 20 fiber. And that had minimal traction within the industry because of the cost as well as the amount of fiber that was required to be able to support that solution. So what is happening is that in 2015, with the emergence of the 802.3bm standard, we now have electronics that are going to be using 25 gig electrical lanes coming off the host chip out to the front plane where the pluggable modules plug in. So now I can have 2 lanes coming in to support 50 gigabit, or I can take 4 lanes to get to 100 gigabit. So now I can reduce my overall fiber counts from 20 fibers for multimode down to 8 fibers to be able to support 100 gigabits there. And there's current activity going on within Ethernet to be able to support 40 gigabit using 16 lanes of 25 gig in both directions. I'll comment on 40 gigabit as we get further down through the presentation. And then on the OIF roadmap, they're now working on 56 gigabit electrical trace guidance that would support 50 gigabits. They're looking at 2 means for supporting that. One is with NRZ, non-return to zero, where you have 1 bit per symbol period, and the other one would be with PAM4, which is called multi-level encoding, where you would have 2 bits per symbol. So with that, you can see what the capabilities are for the higher data rates and the number of fibers for requiring that. So in response to the servers and the emergence of these higher data rate speeds, this gives you an understanding of the I/O speeds that are being configured into the servers. So in the light orange tan color, you can see that's 10 gigabits. So you can see that the 1 gigabit which is coming down over time, and you see the emergence of more and more 10 gigabit actually being deployed on the servers. Up to this time, most of the 10 gigabit interfaces on the servers have been twin-X cable that plug in with an SFP plus twin-X cable that has 3 to 5 meters distance capability as a passive twin-X, and we also have had some active optical cables that plug into them as well. But you start seeing 40 gigabit come into play in 2014 and 2015 as the number of VMs and cores on the CPUs continue to increase. And the 40 gigabit, in my impression, is going to be a short period type deployment as standards move on to develop I/O guidance for 25 gig and 50 gig downlinks into the servers. And it will be easier to adopt 25 and 50 gig as interfaces into the server because they are common lane speeds that are used now and in the future to be able to support 100 gig, 200 gig, and 400 gig. So anyway, this gives you a perspective of what the roadmap looks like for the server interfaces that are going to be released over this respective timeline. So looking at the architectures in the data center, what we have seen in the past, looking at data centers configured to run, say, 1 gigabit, is that they would have a collapsed architecture where they would have all the network electronics back in a centralized location, and most all that electronics, 1 gigabit, was adequately served by copper cable at that time. So within the NDA, you would link the switches together with copper. I have optical there, but mostly it was copper. And then you would run these huge clusters of copper cable in the pathway and spaces out into the server cabinets that would then interconnect out into the server cabinet, into the servers. So this is an antiquated architecture that has no migration beyond 1 gigabit. Even if 10 gigabit were put in today to support a distance of 100 meters, there would be restrictions on its ability to be able to support data rates beyond 10 gigabit. So what the industry has done now is migrated to a very flat architecture. This is a very simplistic drawing that shows what a flat architecture looks like. They simply take an uplink from a core distribution switch in the main distribution area that provides typically an OM3, OM4 uplink out to a patch panel that then provides an interconnect down into a top-of-rack switch that then provides downlinks into the servers. In this example that I have here, what I'm showing is a top-of-rack switch in the bottom right that provides for 10 gigabit downlinks into the server. And into the left of that top-of-rack switch, you see 4 slots. And those four slots there support 40 gigabit uplinks that would then support the 10 gigabit drops down. So in the data center, we are really migrating to very low oversubscriptions now and a spine leaf architecture to ensure the overall efficiency and the operating of the networks. Now, I always like to talk about, many people have already deployed chassis switches in their core distribution switch that might utilize 10 gigabit ports. And I always want to reinforce that I can have 10 gigabit ports that can talk to these 40 gigabit uplink ports on the top-of-rack switch. You can combine those 10 gigabit ports and convert them into a 40 gigabit interface that would then plug into that uplink. I have another slide that I'll talk more about on that in a moment. In the image on the right, on the top there, that's a typical type twin-X cable that runs from the top-of-rack switch down into the server. I will say something about 10G-base-T. Up until just recently, we've seen minimum utilization of 10G-base-T in the data center. The reason for that has been due to the high power consumption of the DSPs and the transistor gate sizes that have been used. When 10G-base-T first came out, it was using around 15 watts as they were using 90 nanometer chip technology. That has now migrated over about 5 generations down to technology, I believe, of around 14 nanometers to 20 nanometers. Such that they've been able to reduce the power consumption, I believe, down to around 2 watts. And with that 2-watt capability now, they can incorporate a NIC onto the motherboard so that they have LAN on the motherboard to be able to support RJ45 interface into those servers. So this is an example of an active optical cable. An active optical cable utilizes low performance transceivers that are directly attached onto the optical cable of the specified distance. So what this does is offer a low-cost optical connectivity solution that can be run from a top-of-rack switch down into the server, or something like this could be used for providing an uplink from an end-to-row switch out to a top-of-rack switch as well. Other considerations that are being used in the data center today for top-of-rack solutions is that they'll go ahead and already deploy a 40 gigabit switch at the top of the rack. And in the example here, I'm showing a 16-port 40 gigabit rack mount switch. And today I might have servers operating at 10 gigabits. So I could plug into each one of those QSFP 40 gigabit ports, and then I could break them out into 4 duplex LC circuits that could plug into 10 gigabit transceiver modules on the server. So this provides a very lower cost per circuit solution, as well as a high density solution that could be used. So even though I showed 16 ports here, there are some top-of-rack switches that offer 32 ports of QSFP that can be used as well. And if I have 32 ports, that would provide up to 128 duplex LC 10 gigabit circuits that could be used for plugging in the servers below. And in the image that you see in the middle there, that gives you the lane description of parallel optics. So I'm transmitting on channels on the left, 1, 2, 3, 4, and I'm receiving on channels 1, 2, 3, 4 on the right for parallel optics. But when I have a QSFP that plugs in and I use an MPO into it, on the other end, on the LCs, they break out in the wire mapping where transmit 1 goes with receiver 1, transmit 2 goes with receiver 2, transmit 3 goes with receiver 3, and so forth. So there is a wire mapping mechanism that easily supports the breakout capability supporting that. So a little bit more on the architecture with the spine and leaf. They've gone to a very flat architecture because they want to minimize the amount of latency in the transfer of east-west traffic within the server racks. When you have virtualization, you have your VMs, and if you have high utilization on one server, you can transfer VMs from one server to another server to maximize utilization of these servers as well as do parallel processing. So within the flat architecture, as you can see, they're looking for very low network latency capability as well as the ease of VM movement for east-west traffic movement. And most people are probably quite familiar now that when you look at within the data center now, east-west traffic movement within the servers, it's going to represent 75 to 80% of the traffic flow within the data center, where the north-south traffic will be 25 to 20% of that traffic flow. In the past, before we had server virtualization, the north-south traffic flow actually represented the 75%, and the network traffic within the data center only represented about 25%. So the other interesting thing about this is that there's no oversubscription on the uplinks from the distribution core switches out to the edge. Everything's one-to-one oversubscription. And as I alluded to earlier, we have very low oversubscription into the servers as well. That can range anywhere from 2-to-1 to 4-to-1 to 5-to-1 oversubscription. And also with this flat architecture, the use of spanning tree for overall management is replaced by the port management system of, the spanning tree port management maintenance is replaced by the use of Trill. So this is an example, a nice illustration of what a spine and leaf architecture looks like. It's typically 2 layers. So you have the spine, which could be the core layer or a distribution layer that is fully meshed out to the top of the rack switches, or it could be meshed into an end-of-row switch that would provide uplinks out to the servers, or it could actually go into a 3-tier system where all the distribution core switches would be meshed to a distribution switch that would then provide uplinks to top-of-rack switches that would then feed down into the servers. What we normally see is the image on the right is what you would see in very large mega data centers where they would feed from the core out to a distribution point where we have server pods, and in that server pods you would have distribution points that would be meshed to the top of the rack switch for the east-west traffic movements. So moving on to other technology that's being used in the data center to ensure the overall reliability of the transmission systems. In the past, networks would rely on what they call port mirroring to evaluate and track the overall performance of their networks. But with the emerging of cloud service providers as well as government regulations, we now need to be able to actually evaluate in real time the conditions and the operations of the transmissions of the networks within the data centers. So what is happening now is that instead of using port mirroring, we're now using optical passive tap modules. And this technology is very similar to what is done for fiber to the home, the Verizon type networks, where you take an optical signal, you run it into a splitter, you do something like a 70-30 split, so 70% of the signal goes on through, and 30% of the split is then transferred down into a protocol analyzer that gives you a real-time evaluation of what the transmission of the network is and how it's performing. So you can see on the right there is for some of the reason as to why people are starting to implement this. One is obviously for security and performance. One is for OpEx savings, because you can track the overall performance of your network. You might be able to detect the slow deterioration of performance over the time that allows you to schedule time to go over there and make maintenance changes as necessary to bring it back up to where it's supposed to be. But also we have service providers and colo data centers to be able to have the means of demonstrating reliability to meet their service lease agreements, as well as we all know about service regulations or government regulations that have to be met as well. So looking on at data center fabrics, in most data centers today, we have the network side, which is the LAN side, which is Ethernet, and then we also have the storage area side, which is fiber channel. And then some data centers, which also have the LAN and the SAN, some of them do have a high-performance computer clusters that use InfiniBand, but we don't really see much of that. Most of the InfiniBand we see used in traditional type data centers are using that for low latency frequency trading. So on the network side, here is a glimpse of the existing Ethernet speed roadmap and the standards that have been developed. So we take you all the way from 10 megabits all the way up to the emerging 400 gigabit standards that's under process right now. So you can see what the dates are and what the respective lane speeds are. So just this past month, we had the new 100 gigabit BM standard that was approved. So that will be in another slide that I'll be showing you. But the 100 gigabit that you see right here, this is based on the 10 gigabit lanes. And the 40 gig is based on 10 gigabit lanes. And then you see the activity that's taking place with the 25 gigabit. And also you see the 400 gigabit as well. So here's another glimpse of activity on the Ethernet speed roadmap. You see the 2.5 gig and the 5 gig on the speed roadmap. This is activity directly focused at copper cable for supporting uplinks into wireless access points to be able to support 1 gigabit operation on those devices. So that's pretty much exclusive to that and has really no impact on data center utilization. We will be looking at 25 gigabit activity in the data center to be able to support the 25 gigabit drops down into the servers. I didn't say earlier, but I will say that the server roadmaps now are going to be based on 10 gigabit now, then 25 gig, then 50 gig, and then 100 gig. I see, and I said earlier, that over time I don't really see a long continual adoption of 40 gigabit to the servers, as they'll be replaced by 25 gig and 50 gig. So you see the completion date for the 2016, and there's 50 gig, and then coming down you see the 100 gig that I mentioned in the previous slide using 25 gig lanes. This was just approved this month, and I probably expect to see the standard sometime out very, very soon. So a review of the different 40 gigabit roadmap solutions. You see at the top there's the twin-act solution. It's a passive copper cable shielded solution that goes 7 meters. We have the multi-mode OM3, OM4 solution using parallel optics for 40 gigabit SR4. You know, people have asked me, I discussed with you why 40 gigabit using 10 gigs doesn't go 300 meters. I told you they use 10 gig optics on their lanes, but the 10 gig optics have a lower performance than what is used with the traditional 10 gigabit 10G-based SR. But the reason why they went with parallel optics at 40 gigabit at the time that this standard was developed is that the standard technology at that time wasn't enabled to be able to support direct modulation out to a 40 gigabit data rate. At the time that this was going on, I don't think the VCSELs technical capability was more than around 22 gig. And they also considered the use of CWDM, but they decided that parallel optics offered the lowest cost variant to be able to meet 40 gigabit multimode service. So you can see there the 100 and 150 meters. We are really starting to see a significant amount of 40 gigabit being deployed in enterprise data centers as well as hyperscale data centers, both for multi-mode and single mode. So that's what you see on the next there is LR4, which is a single mode using duplex fiber. The FR solution is a single wavelength 40 gig. They're just finishing up an ER4 solution on duplex single mode fiber that goes 40 kilometers, and they are working on 40G base T. Some of the characteristics of the Cat-A cable, I think this is specified out to 2 gigahertz. It's the bandwidth operating spectrum. It supports a distance of 30 meters, but only 2 connector pair. Commercially available products out there. There are multiple companies that offer 40 gigabit solutions that do utilize 10 gigabit lanes that follow the 10G base SR standard. So if you go back and use 10G base SR 10 gig optics, you can see that I'm able to achieve 300 meters and 400 meter distance capabilities based on standard connectivity assumptions. And you can see that with certain connectivity solutions such as Corning, you can achieve extended reaches as well of 330 and 550 meters on OM3 and OM4. You know, we just recently completed some link distances for multi-mode and single modes in the data center. And what we show for multi-mode fiber is that 100 meters represents around 93% of the deployed links within the data centers. So there are a few samples that are needing these extended reach transceivers to meet some needs out there versus having to go to higher cost single mode optics to provide for these extended reach capabilities. Other 40 gigabit options out there that are being considered for use is that many people out there have legacy LC connectivity deployed in their data center, and some people also really are not quite fond of using MPO connectivity for interfacing into their transceivers and are going to a technology called 40G base short wavelength BiDi transmission. And in this scenario, instead of using MPO connections into the transceiver, we are using duplex LCs. And in the diagrams that you see on the right, on the top you see the traditional type transmission for a parallel optics type solution. We have 4 10 gig electrical lanes on the left that feed into the transceiver that then drive 4 lanes of optical solutions to the other end, and just the opposite, in the other direction. On the bottom, you see the bidirectional solution. You still have the same electrical interface for the QSFP that plugs into the slot. So you have the 4 10 gig electrical lanes, and in the technology of the transceiver, they combine 2 of the lanes, the 2 10 gigabit lanes, to create a 20 gigabit electrical lane that is used for driving 2 optical signals in the opposite direction at 20 gigabit. And then they're transmitted over the fibers in opposite directions. So other optical solutions for 40 gigabit using duplex fiber is that recently a company has announced the use of a single mode launch into multi-mode fiber using the 40G based LR4 wavelength plan that you see on the bottom. So they're simply just doing a single mode launch using these multiple wavelengths operating across that wavelength spectrum. And on the left there, it gives you an understanding of what the distance capabilities are with the OM3 and OM4 fiber. Another unique attribute of this transceiver is that not only does it work on multimode fiber, since it's a single-mode launch, it also works effectively on single-mode fibers of OS1 and OS2 to 500 meters. So in some terms, you could call this a universal transceiver that can be used both on multimode and single-mode fiber in 1300 nanometer region. Glimpsing at the 100 gigabit roadmap, you can see that we're now down, just completing, as I said earlier, the 100G base SR4 standard. This is using 25 gig electrical lanes. That's what the -4 means there. We have 4 lanes that are coming down off the chip that are feeding into the transceiver module to drive 4 lanes at 25 gig on multimode fiber in one direction and the same in the opposite direction. So the distances there are 70 and 100 meters. And this standard, as I said earlier, has been completed. So when they were working on the BM standard, these were the objectives that they were looking at to meet the needs of the industry. They were looking at both multimode and single mode. You can see there that they also included a 40 gigabit. So they just adopted the 40 gigabit because they were just trying to extend the 40 gigabit out to 30, 40 kilometers. So that was just integrated as part of this standard just to have some place to put it. But the focus of the document was, from our perspective in the data center, was mostly geared towards the 100 gigabits for optical connectivity. So in the second sub-bullet there, they wanted to initially come up with a 100 gigabit solution for single mode up to a distance of 500 meters. And multiple solutions were considered. They looked at a parallel variant, they looked at a WDM variant, and they looked at a duplex fiber variant using multi-level encoding. And because there was a diversion of such interest in all these solutions, it was unable to achieve a 75 voting member support to adopt any of these variants or PNDs into the standard. So because they weren't able to achieve a 75% support, none of this guidance was included in the standards, and these groups had to set up proprietary MSA groups to develop guidance, but I'll show you what that is in a moment. The one objective that did go through to yield results within the standard is, you can see here, 100 gigabit PHYs that operate up to 100 meters on OM4, so this was the parallel optics using 8 fibers. They also considered the use of a low-cost variant of multimode fiber to 20 meters, but the determination was made that there wasn't a significant enough economic value prop to include transceiver solutions in the standard. There just wasn't that big of an economic difference in the price of a transceiver at 20 meters compared to what you have at 100 meters, so there wasn't enough support to justify the inclusion of that within the standard. Oops. So this gives you a 100 gigabit transceiver roadmap. The first generation of 100 gigabit that came out, again, was using the 10 gigabit electrical lanes that you can see in the top. So where they say 10 by 10 gig, those are the electrical lanes that are feeding into the electrical interface of the transceiver. And the first single mode transceiver that came out was a CFP transceiver, and it was a very large device. It consumed around 20-25 watts of power for it. And the reason for that is that it had to put a gearbox in it that would aggregate the 10 gigabit electrical lanes on the way in to convert them into 4 25 gig electrical lanes that would then drive the WDM optics and just do the reversal on the return path. So this device really had minimal traction within the industry. And the first multimode solution transceiver was the CXP. Once again, this took 20 fibers, and it required the use of a 24 fiber MPO interface into that device. In 2013, they migrated the CFP to the CFP2. Essentially what they did was they took the gearbox out of the CFP and they put it on the host card of the electronics, such that the aggregation of the 10 gig electrical lanes could be done on the host card that would then feed into the transceiver. And in 2015, we now have the state-of-the-art transceivers that are going to be used for 100 gigabit. And the transceiver that's going to be that will win out in the in the data center space is going to be the QSFP because it offers the smallest form factor that provides for high density line card solution. It also has for a 3.5 watt dissipation capability. It can be used either for parallel optics or it can be used for duplex fiber transmission on single mode as well. The CFP4 is mostly going to be a carrier type solution because they're using optics that require much higher power to drive signals longer distances. So the CFP4 is a larger form factor and has higher power dissipation capabilities. So moving on to 400 gigabit. So the study group adopted in 2013 these 400 gigabit objectives, 100 meters on OM4, 500 meters over single mode, and so forth. So there's been agreement on the solution for the multimode fiber being 16 lanes of parallel optics in both directions using 32 fiber MPO. But to date, it's my understanding they're still trying to determine what the single mode variant PMD-PHY is going to be. So this is a projection of 400 gigabit multimode fiber variants. As I just said, the first generation solution will use 32 fibers. And expectation is that this will have very minimal traction within the industry. And what it will be used, expectations are, will be used as an active optical cable assembly that will be used for interconnecting routers within the data center. So in no way is anybody expecting a 32 fiber connectivity solution to be used for uplinks from the core out to the edge. And the timeline on that, as you can see, is 2017. The second generation would move on to using 50 gigabit lanes. And with 50 gigabit lanes, that would reduce the fiber count down to 8 in each direction. And with 50 gigabit, that could either be some form of NRZ, or it could be a WDM, or it could be some form of multi-level encoding operating at 25 gigabaud. Once again, we do not expect any form of base 16 fiber cabling being deployed in the data centers to support this type of connectivity solution. We expect this to be used once again as an active optical cable solution that would be used for interconnecting routers in high-density applications. What we do see is the emergence of 400 gigabit in the multimode fiber coming for uplinks in the timeframe of 2024. And at this time, we see that we'll be seeing 100 gigabit lanes with 4 fibers in each direction, so aggregates of 400 in both directions doing that. We believe the capability of this will be enabled with 50 gigabit and weight division 50 gigabit with WDM and PAM4. So this is a futuristic roadmap. I think it's pretty good. This slide provides you what the electrical lane speeds are and what overall data rate it enables you to be able to support. So it takes you from the first generation 40 gig and 100 gig, and it gets you out to a speculation of terabit speeds that you can use as a future reference point for consideration. Okay, moving on to fiber channel. This is their speed roadmap, and I'm not going to go through each one of these, but what has been done is just recently we have finished the 32 gigabit fiber channel. And in the fiber channel world, 95 to 98% of all the connectivity used there is OM3 and OM4 fiber, and the rest of it is single mode, and that single mode is used for synchronization between data center sites or in campus environments. There's no copper at all being used in the fiber channel world. It's all optical connectivity. So once again, the 32 gigabit has just been concluded. This standard will probably be coming out in the next month or so. But because the VCSEL technology had progressed to the point it can be able to be directly modulated out to 28 gigabit for 32 gigabit, we have a duplex fiber serial transmission for 32 gigabit. An activity that's coming to closure right now within fiber channel is a parallel optic solution for the first time. We are going to offer 128 gig, which is equivalent to 4 by 32 gig in both directions using 4 fibers. And the big play for the 128 gig is in support of breakout capabilities. The electronic industry is moving to the use of very high data rate ports that support breakouts to lower data rates to help drive up the number of circuits per line card and help drive down costs. We are now going to be emerging or growing or moving to the use of 64 gig in fiber channels, the next developing standard. The marketing resource requirements for that have been defined and will be commercially available or released to the public in the near future. And then we also have 256, which is also a parallel variant 4x64. So this is the speed roadmap for fiber channel or Ethernet. So this is all about convergence. A lot of people want to use Ethernet for conveyance of all transmission systems within an Ethernet frame. So this first evolved with 10 gigabit fiber channel over Ethernet. And this technology essentially takes a fiber channel frame, encapsulates it inside of an Ethernet frame, and then uses an Ethernet switch for conveying that signal from one point to the next point. Presently, I haven't seen this technology getting wide adoption within the industry. People are still maintaining their separate networks of the Ethernet fabric and the SAN fabric with the fiber channel. But where it is being deployed is mostly just staying within the server rack, where you'll have an Ethernet downlink into a converged network adapter card, a CNA card. You go in with Ethernet, and then you come back with fiber channel that's encapsulated by the Ethernet frame that then goes back up to the Ethernet switch for conveyance. But you can see what the speed roadmap is here. We just finished the 40 gigabit FCOE guidance. The others will be coming in the future. Well, you can see the 100 gigs available as well. So these are some discussion points about 32 gigabit. And I told you earlier about the electrical distortions that can happen across the trace from the host chip out to the pluggable module. So you can see in the block diagram at the top, you have to start integrating certain components within the transceiver to correct for these electrical distortions coming off the card. So you have equalizers, and you also have clock and data recovery chips that are integrated into the transceiver to correct for those distortions. So with 32 gigabit, you see the distance considerations there are 70 meters and 100 meters on OM3 and OM4, and it still operates with the utilization of the SFP plus transceiver. Something new with 32 gigabit that I didn't mention with 100 gigabit with the 25 gig lanes is that both of these transmission methods are now using something called forward error correction. So with forward error correction, what that enables is that you're essentially sending the pulse twice, and at the receiving end, it takes the two pulses and reconfigures it into a single pulse that provides reliable performance. But this is the first emergence of fiber channel using the FEC as well as in the Ethernet world for 100 gigabits. So this is just a basic example of how 128 gig is being developed in support of breakout cables. If I have a 128 gig port on the right, I can break that out into 4 16 fiber duplex circuits. I can break it out into 32 gigabit duplex circuits as well, or I can just run native 128 gig from port to port as well. So with fiber channel, this is, with InfiniBand, this is their roadmap. Historically, up to this point, most of InfiniBand has utilized twin X cable and active optical cable. But once we get up to data rates of 40 gigabit and beyond, we start seeing higher emergence and usage of optical connectivity, with twin X only being used in the server racks from the top of the rack switch down into the server. So in their data rate map here, the most widely deployed solution for InfiniBand is based on the 4X line that you see there, and that's analogous to what you see for 40 gigabit Ethernet, 100 gigabit Ethernet, as well as 128 gig fiber channel. This is using 4 lanes in both directions to be able to support that effective data rate. So QDR is quad data rate, so that's 4 times 10 gig. FDR is 4 times 14 gig. EDR extended data rate is 4 times 25 gig. And the high data rate is 4 times 50 gig. So InfiniBand world is now rolling out 100 gigabit solutions now for use primarily in supercomputer environments and high-performance computer clusters. So this is a new vertical opportunity for fiber. As I said earlier, this has mostly been dominated by the use of twin-X copper in 3 to 5 meters. It's restricted to 3 to 5 meters once you get up to data rates of 40 gigabit or higher, so they need to be able to provide for extended reach capability, and optical connectivity offers that capability in the forms that you see there, either as active optical cables, and those active optical cables could either be single mode or multi-mode. The single mode solution could potentially be with silica photonics. They could use pluggable modules, or they could use embedded optics. Similar to what we talked about earlier, in the InfiniBand architecture that are deployed out there uses spine leaf, and point-to-point through the entire network of that spine leaf architecture, the oversubscription is 1-to-1. So that's the end of my presentation. I think some people may have submitted some questions. I don't know. So the first question is, when is the 25 gig fiber connection going to be standardized across the industry? That was on one of the road mapping slides that I provided to you. But I would expect some early adopters of 25 gigs in the servers to happen within the next 12 to 18 months. Can we get a copy of this presentation? Yes, the presentation.
I think, yeah, Liz has already addressed it. That can be downloaded, correct, at the end of the presentation. I'll let Liz follow up on that. Okay.
And also, once we get rid of this screen, I'm going to put my email up. So if you have any questions in the future, you can always send me an email as well. I'm trying to read. With regards to the evolution of optical interconnections, transfer with the distant transfer.